Let us try to understand property of XNOR gate. XNOR gate is written something like this. Sometime it is XNOR or exclusive NOR. So whichever is your choice, you can use that. So the logic symbol of XNOR gate is it's a XOR gate followed by a bubble. This bubble is nothing but equivalent to a NOT gate. And the symbolic notation for XNOR operator is it's a dot inside a circle. So XOR is it's a plus inside a circle, XNOR is it's a dot inside a circle. So the logic symbol of XNOR is this one, and you can write this output as A XNOR with B. That is A XNOR means dot inside a circle B. And this is what the truth table is. Like the way we understood XOR gate, how it produces output 1. So here the logic is whenever you have a XNOR gate, you count how many number of 0 are there. If number of 0 are even, the output will be 1, else it is 0. So here you see this is the logic. Output logic is 1 if there are even number of 0 present in input combination, else its output is 0. So in the first case, 0, 0, how many 0 are there? 2 number of 0. 2 is a even number? Yes. So there are even number of 0 on input side, output is 1. Here there are 2 number of 1s on the input side, 2 is a even number, so output is again 1. So here 1 number of 0, odd number of 0, output is 0. So here 1 number of 0, odd number of 0, output is 0. So you observe, student, here one thing, that the output of a XNOR gate is logic 1 when both inputs are same. So if you observe in a 2 input case, whenever both inputs are same, you are getting the output as logic 1. So that's why XNOR gate is sometimes known as equality detector. So XOR gate was inequality detector, XNOR gate is equality detector because it produces output 1. Whenever somebody is saying that output is logic 1, it means that the inputs applied are same. In case of XOR gate, when the output was 1, we say that the inputs applied are not same. So in this case, output is 1 when inputs are equal. That's why it is called the equality detector or coincident detector. So the logic expression of XNOR gate is y of AB is equals to A bar B bar plus AB. So if you observe the mean term notation, it is 0 0 A bar B bar and here it is AB. And if you observe the max term notation, here it is A plus B bar and here it is A bar plus B. So both of these are equivalent things. So this is the mean term notation, this is the max term notations. So like we have seen the inverter and buffer application of XOR. So this is also your inverter and buffer application of XNOR. So what it says is, if you observe the property A XNOR with 1 is A. So here it is A and this is 1. So A XNOR with 1 is A. So whenever if you are fixing one of the input to 1, then whatever you are giving in the other input, the same thing is transmitted to output. So this is nothing but the buffer application. But if I am making one of the input A, other one 0, so A XNOR 0, you get it is A bar. So this is nothing but your A bar. So here, if one of the input is fixed to 0, whatever you give in the other one, you are getting its complement. So we call this is the inverter application of XNOR gates. So it is opposite. In the XOR gate case, if you remember, when one of the input was fixed to 1, you are getting A bar. When one of the input was fixed to 0, you are getting A. But here it is opposite. So if you want to work a XNOR gate as buffer, you fix one of the input to 1. Then whatever you give in the input, so you get the same thing as the output. You want to make it as a inverter, you fix one of the input to 0, then what you give in the other one, you get the same, it's complement at the outputs. Alright, so these are the property, students. Like we have seen the property in case of XOR like this. So its equivalent property in XNOR are like this. So how does this happens? You can again make use of this relation. For example, if you ask me, sir, how A dot 0 is A complement? So in place of B, you substitute here 0. So y of A comma 0 is A bar B bar, A bar 0 bar plus AB, A dot 0. So this is A bar dot 1 plus 0, so you get it is A bar. So A XNOR 0 is A bar. Same thing. I mean, you can try all these things here by substituting the corresponding value of B. You can take these are the value of B and if you put it here, so whatever the answer you will get, so this is what I have written. So earlier case, in case of XOR, A XOR 1 was A bar, right? A XOR 1 was A bar, but here A XOR 1 is A. Similarly, A XOR 0 is how much here? A bar. A XOR A is 1, A XOR A bar is 0. So you know that whenever both inputs are same, output is 1. So it means that A XOR A is expected to be 1. Whenever both inputs are not same, output will be 0. Right? So if a variable complemented to itself, that means they are not same, the output should be 0. This way you can memorize this. And students, these property are something known as the special property. Okay, so which are linked with both XOR and XNOR. So I have A XOR B. Listen carefully the logic I am telling you. No need to memorize this individually. So I have A XOR B. So what is the concept is, if one of the variable is complemented, then XOR become XNOR. In other words, A XOR B is there. So here I am, what I am doing is I am replacing A with A bar. So if I am replacing A with A bar, so if I am replacing A with A bar, so how much you get? A bar XOR with B. So this is equivalent to A XOR B. That is what my point is. You have A XOR B. In that, if you complement one of the variable, then XOR will change to XNOR. So if you are complementing this variable, then A bar XOR B will be equivalent to A XOR B. So not necessary that I have to complement A. If you complement B also, you get the similar thing. That is, if you find what is A XOR B bar, the answer is it is again A XOR with B. But when you complement both variable, XOR remains XOR. In other words, you complement both variable. Now you replace A with A bar, you replace B with B bar. So this answer will be again A XOR B. So whenever in the XOR gate, one of the variable is complemented is equivalent to XNOR. When both variables are complemented, it is equivalent to same XOR only. Same story is applicable for XNOR also. So these things are written here. A XOR B bar is equivalent to A XNOR B. A bar XOR B is equivalent to A XNOR B. But A bar XOR B bar is equivalent to A XOR B. Same thing here. A XNOR B bar is A XOR B. So if you have A XNOR B, if you complement one of the variable, XNOR become XOR. So A XNOR B bar is A XOR B, or A bar XNOR B is A XOR B. But when you are complementing both of the variable, it is same XNOR only, A XNOR B. Okay, so I'll show you using this property how beautiful way we can solve certain questions. Okay. Next thing, student, is whenever I have some operations regarding XOR and XNOR, I have to find the complements. So De Morgan's law we have studied in Boolean algebra. So how it happens? But De Morgan's law, it is not exact De Morgan's law. You can think of this is something similar to De Morgan's law. Whenever you have a XOR operation like this and you have complement, if you want to remove this complement, you do the same thing. That is, you complement every variable and replace the plus by dots. So replacing plus by dot is equivalent to replacing XOR operator with XNOR operator. So all variable will be complemented and XOR will be replaced by XNOR. So it is A bar, it is B bar, C bar, D bar. So these should be separated by XNOR, which was earlier XOR. Similarly, when it is A XNOR, B XNOR, C XNOR, D, if you are finding its complements, so you complement each variable, A bar, B bar, C bar, D bar, and XNOR will be XNOR operator will be replaced by XOR operator, like this. So this is kind of De Morgan's law. Okay, so let us see using this how can we solve certain questions. So let us first solve this one. So for this, let me copy the property so it will be easy for me to explain you. So this property I need to solve this problem. And okay, and I also need the XNOR property, this one. And along with this, I also need this setup property. Okay, see. So here the question is simplify the following. Okay. So how do you simplify this? So I want to start with this one. So this can be rearranged like A XOR. So let me interchange the position of this. A XOR B is equivalent to B XOR A. So it doesn't matter if you interchange the position. So it is A XOR A bar XOR with AB bar, right? So XOR gate satisfy associative law. So if you want to do XOR of any two, so no problem. So this is A XOR A bar. Now what is A XOR A bar? A XOR A bar is 1, this property. So this is 1. So 1 XOR with AB bar. 1 XOR with AB bar. But what is 1 XOR with A? 1 XOR with A is A bar. So 1 XOR with AB bar will be complement of AB bar. So by De Morgan's law, if you split it, you get this is A bar plus B. So this answer is A bar plus B. Okay, what I did first, I interchange this. So if I'm interchanging this, I got this. Then you got your AX or A bar. AX or A bar is 1. So using this property, so it is 1 XOR AB bar. 1 XOR AB bar is equivalent to 1 XOR A is A bar. 1 XOR AB bar is equivalent to AB bar complements. By De Morgan's law, it is A bar plus B. So using this property, how easily we are able to reach this conclusion. Otherwise, if you don't know this property, you have to expand this like A bar B plus AB bar. Whatever the answer you got, again you have to expand this with respect to A bar, which is a very tedious task. All right. Now, student, you see that this is A XOR B. This is a XNOR operator and is A XOR B bar. So this I can write this as A XOR B. Okay. XNOR with what is A XOR B bar? A XOR B bar, if one of the variable is complemented, it is equivalent to XNOR. So A XOR B bar is equivalent to A XNOR B. A XOR B bar is equivalent to A XNOR B. A XNOR with B. So this is A XOR B and this is XNOR with A XOR B complement, because in a two variable case, XOR and XNOR are complement to each other. In other words, if you compare this table, which is 1001, and here it is 0110, that means if you take complement of this, you are going to get this table. So A XOR B is equivalent to A XNOR B complement, or A XNOR B equivalent to A XOR B complements. So that's why in place of A XNOR B, I am replacing with A XNOR B whole complements. So this is equivalent to, so you see this is like a variable X and this is equivalent to X bar, right? So this is same as this one, right? So if you take this is X, you can say this is your X bar. So X XNOR with X bar. What is a variable, XNOR with its complement? The answer is 0. So X XNOR with X bar is definitely 0. So answer is 0, right? So this answer is A bar plus B we got, and for this the answer is 0. So this is how you have to deal with. So just by knowing the property, we are able to reach the conclusion. Otherwise, it will be a tedious task to reach the conclusion. So here, this is one of the CS problems, student. You see that, so they're asking us to simplify this expression. You see how many number of XOR has been used, 5 to 6 times. And every time if you think like you have to expand it and you have to solve, you will be nowhere, right? So this kind of problem has to be solved using the properties. So one by one, let me do. So first thing is 1 XOR P. So what is 1 XOR P? So this bracket, so how do I write it? Okay, 1 second. So 1 XOR with P can be written as P bar. Like 1 XOR with A is A bar. So 1 XOR with P is P bar. P bar. Then you have this XOR. So I'm writing this XOR. Then you have P XOR with Q. So this is what I have written here. So this I have replaced it by P bar, then XOR, then it is P XOR Q. Then you have one more XOR operator. So this operator I have written. Then I am starting a square bracket. Then you have P XOR with Q, XOR with. You see this is Q XOR 0. So A XOR 0 is A. So Q XOR 0 will be Q. So if you want, you can put a bracket. The bracket is present here. So here the bracket is present here. But it satisfies associative law. It doesn't matter in what sequence you solve this. So as per my requirement, I can put a bracket here and I can put a bracket here. If I do it, so P bar XOR P, A XOR A bar is 1. So the last property, A XOR A bar is 1. So P XOR P bar is 1. 1 XOR with Q. So this is one bracket XOR with. This is P XOR with. This is Q XOR with Q. So what is Q XOR with Q? Q XOR with Q will be 0 because A XOR with A is 0. So similarly, Q XOR with Q will be 0. So this is equals to 1 XOR with Q is Q bar. 1 XOR with A is A bar. So 1 XOR with Q is Q bar. This is XOR with P XOR 0. P XOR 0 is P. So P XOR 0 is P. A XOR 0 is A. So P XOR 0 is P. So this is equivalent to P XOR Q bar. So P XOR Q bar is equivalent to P XOR with Q. How I am saying this? P XOR Q bar, A XOR B bar is equivalent to A XOR B. So P XOR Q bar is equivalent to P XOR Q. And we know that XOR XORs are complement to each other. So P XOR Q can be written as P XOR Q whole complement. P XOR Q is P XOR Q whole complement, which is given in option D. So D is the right answer for this question. Yes or no? So just by effective use of this standard property, we are able to reach this conclusion. Otherwise, this will also going to take at least 7 to 8 minutes of time. But again, I'm explaining you. That's why I have taken 3 4 minutes of time. But you solve this in a proper flow, so it will not take much more than 40 to 50 seconds to reach the answer. So answer is option D. All right. So this question is asked in Gate Electronics 2002 students. The question is, if the input to the digital circuit in the figure consisting of a cascade of 20 XOR gate, then what is the output Y is? So this is X, and this X is common to all the 20 gates. So total there are 20 number of gates. So what is output Y? Okay. So we have seen that this, if you observe, this is 1 XOR X. One of the input is 1, other input is X. So what is 1 XOR X? 1 XOR X, we have seen it is X bar, right? 1 XOR X is 1 XOR A is A bar. So 1 XOR X will be natural, it will be X bar. So this is your X bar. Now, if you see the second gate, so the input is X and X bar. So to this XOR gate, the inputs are X and X bar. So if the inputs are X and X bar, you get the output as 1. Now, for the third gate, the inputs will be again 1 and X, because you got this output as 1 and other is X. So 1 XOR X will be X bar. For the fourth gate, the input is X and X bar. So what is happening is, to the first gate, to the third gate, to the fifth gate, for all these odd index gate, that is 19th gate, for all of these gates, the inputs are 1 XOR X. So the output will be always X bar. But for second gate, for the fourth gate, sixth gate, like this up to 20th gate, what are the inputs? Like the second gate, you see the inputs are X bar and X. For the fourth gate, it is again X bar and X. So it is X bar XOR with X. So X bar XOR with X is 1. So here you are supposed to find the output of the last gate. That is, this is the 20th gate. So it will be definitely your 1. Answer is option B. So like this, some logical questions are framed, students. Unless until you don't have good grief on the property of XOR gate, it might be very challenging to answer this kind of questions. Challenging in the sense, it will be quite time taking. That's all. I'm not saying that you cannot answer, but it will be always time taking, right? So this is what the thing is. Now, let us see some more interesting property of XOR and XNOR.